So, as you know from watching the video already, calculus is the mathematics of change. And the tiny building block of all of the things that we're going to do in calculus is the limit, okay? And you may have already seen a little bit of an intro to limits, but that's what we're going to talk about here. Is we're going to talk about notation and then some different approaches to how to do limits, okay? So first of all, let's talk notation so that when we see a limit expression, we know how to read it. So here's two written examples of limits. This one's generic. This one has a function in it, okay? And so when we read this, we're going to read this one of two ways. Both of them are equally correct. I usually say the second one, but it doesn't really matter. So when I read this, I say the limit as x approaches c of, and then there's a function in here. So of, in this case, f of x is, and then capital L is the limit. Okay, so whatever goes on the right side here, this is the limit. The limit is a value. Okay, it is a value that a function is approaching. Okay, so on the second one right here, we would say, you could read it the other way too. You could say the limit of the function 2 minus 2x, well, you don't have to say the words the function, but the limit of 2 minus 2x squared over x minus 1 as x approaches 1 is 4. Okay, so we have a function inside the limit, and we have a value that the variable is approaching. In this case, it's a 1. Over here, it's a c. And then the limit, the value of the limit is what goes on the equal sign. Okay, so what that means is you cannot write, let's make up a number here. This does not mean anything. We can't say the limit as x approaches 4 of equals 7. Okay, it doesn't make any sense. We have to have a function in here. Just like we can't write f of and then have that be equal to. We need equal to something. We need to have something in there. Okay. Likewise, you cannot write a limit without anything under it. So you can't write the limit of x squared plus 9 equals 5. Something like that does not make sense. So don't do any of this stuff. You do need to be able to use correct math conventions, meaning notation and such. So please make sure that you are being careful with that and not lazy. Okay. All right. So that's our notation. Now, as far as what this means, let's look at this first example here. We have the graph of some function, and we want to know what is the limit of that function as x approaches 2. Okay. So what that means is, as x is getting close to 2, so x is on your horizontal axis, okay? So as we're moving horizontally, we want to know what is the function approaching as our x coordinate gets close to 2. So remember, every point has an x and a y coordinate. So at this point right here, x has we have an x coordinate of 1. This ordered pair right here, x coordinate of 3, okay? As we move closer and closer to x equals 2, which happens here, we want to know what does f of x approach. And remember, f of x is the output of the function. In other words, the y coordinate, okay? So as x gets close to 2, what does y get close to? And we can see here, this point right here tells us that we are getting very, very close to 3. Okay, so here the limit as x approaches 2 of f of x is equal to 3. Okay, all right, and we'll talk more about the definition here in a second, but let's go to this next one. Okay, so here g of x, we're defining a new g of x as f of x when x does not equal 2. Okay, so g of x is going to look exactly the same, except x equals 2 is not part of the domain, meaning that I'm going to have a hole right here. Let me make that a little bit bigger. I'm going to have a hole right here, okay? And then everything else is pretty much the same, something like that, and this part doesn't need to be perfect. Okay, something like that, because really we only care what's happening right around 2 right now. Okay, so now, what is the limit as x approaches 2 of g of x? Well, on here, when we look at 2 comma something, we notice it doesn't have anything. That does not mean, though, that the limit doesn't exist, because this is the important thing about limits. Limits do not care what is happening at a point. They only care what is happening around a point. So we only care about what's happening right, oh, that didn't change. What's happening right here and what's happening right here. What are we getting close to? Remember, it doesn't say what does g of x equal, g of 2 equal. It says as x gets close to 2, what does g approach? What does it look like it's getting close to? And we can see that from both sides, we still approach a height of 3. Okay, so the limit here is still 3. You could also put L equals 3 if you want. Okay, or write out the whole expression like we did over on the left. Okay, so here the limit is still 3. All right, one more thing on this example. Now we're going to graph h of x, and so h of x is the same as f of x when x does not equal 2, but then it's equal to 1 when x does equal 2. And I'm going to put that right on top of the same graph because it's not going to change. It's not going to change my picture. Okay, so when x equals 2, h of x is equal to 1, which is right here. Okay, so now all of this is the same. Okay, still have an open circle here. All of this is the same, but we have a point right here. So now what does the limit as x approach 2 equal? Okay, well, in this case, again, we're still looking at the behavior around it. And my strong recommendation when you're trying to figure these out is actually put your fingers to, I mean, you can't see that I'm doing this, but put your fingers to the left and to the right of x equals 2 and slide them along the curve that you have along your function and see where your fingertips just about meet, okay? And in this case, we see that the limit is still 3, okay? Again, limits have to do with what is around a point, not exactly at a point. All right, so let's give an intuitive definition. This is just our intuitive understanding of what a limit is, okay? And we're going to write this as x gets closer and closer to c, f of x, so the input, and then x is the input, f of x is the output. F of x gets closer and closer to L, okay? But there's 2 important pieces to add to this. Very important. Like this important. Big time important, all right? And those are that we have to add from both sides, as in from the left and from the right, and I'll show you the one-sided stuff here in a second, okay? So from both sides needs to be added to the end of that, our intuitive definition. And also we need to add that the limit does not care about f of c. Okay? Does not care. Can't stress that enough. It does not matter what is happening at the point. Okay? In other words, if I have a function and I want to say, well, what is the limit as x approaches 12? Well, let's just plug 12 in and that must be the limit. No, it does not matter what is happening at the point f of c, c comma f of c as an ordered pair. Okay? All right, now we do have such thing as one-sided limits, and the difference with the notation is we have this little plus sign or a little minus sign, and it's a superscript. It's up and to the right of whatever constant goes down here. If you see a plus sign, then this means we have a right-sided or a right hand, whichever way you want to say it. Okay, and this is a left side. In other words, that means we only care about what the function is doing as we come from the right or from the left. Okay, so like if this is our point at C, we only care about what the function is doing as we come from the right or as we come from the left if we have a little minus there. Okay, now in order for the limit of a function at a point to exist, this needs to be true. We need to have the limit from the left and the limit from the right be the same thing, okay? So this is a theorem, so we can say, we're not going to prove this theorem, but it is a theorem, all right? Some theorems we will prove this year, okay? And if you remember from geometry, a double-headed arrow like this means if and only if. It's also abbreviated IFF. Okay, means if and only if, so I'm going to use those for some shorthand here. Okay, but we're going to say the limit as x approaches c of f of x is equal to L if and only if the limit as x approaches c from the left of f of x is equal to L if and only if the limit as x approaches c from the right of f of x is equal to L. So in other words, in order for the limit of a function with no left or right side, in other words, for both sides to exist, to be equal to L, we have to have that same limit being approached from both sides. Okay, I'm going to do one more graphing example, and then we'll look at it look at limits a different way. All right. Okay, for this graph, before we do that, if you would like to pause the video and take a minute and try and at least fill out this first column on your own, go ahead and do that. Okay. F of negative 8 means, this is not a calculus question, this is just me asking, if I plug negative 8 into my function, what is the output? In other words, I have an ordered pair at negative 8 comma something. And I can get that from the graph. When x equals negative 8, y is equal to negative 5. Okay, f of negative 5. Now, I have an open circle there, but remember, there is no point at an open circle. We get very, 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 very infinitely close, but there is no point at an open circle. Okay, we do have a value for x equals negative 5 down here at negative 4. Okay, then f of negative 3 is 0. F of negative 1 is 2. F of 2, now f of 2 I have another open circle. There is no point anywhere else on the vertical line x equals 2, so that means f of 2 does not exist. Okay, f of 7, here again I have an open circle, however I do have a solid point right here, so f of 7 is not negative 5, it's positive 3. And then f of 10 also does not exist because I have an open circle. Oops. Does not exist, okay? And then for the limits, okay, now imagine that we're putting our fingers to the left and the right of the given x coordinate here, and we're moving along the function towards that. If our fingers do not meet, then we do not have a limit because we need to have the same thing from the left and the right. So if I want to put my fingers on the graph to try and approach negative 8, I can do that from the right, but there isn't anything to the left. And since I cannot approach x equals negative 8 from the left, then that means this limit does not exist. Okay? Now, can I approach negative 8 from the right? Yes, I can. I would be moving this direction. Now, I'm moving from right to left, but if I follow along the curve, I do this, and it approaches this point down here of negative 5. Okay? And then for negative 5, the limit from the left, well, if I put my finger over here, as x approaches negative 5, I approach. Now, I don't reach it because there's an open circle there, but again, the limit does not care what is happening at the point. Just cares about what's right around it, so just right here. Okay, and you're going to hear me say that a whole bunch of times. We are approaching 2. Okay, and then if we approach from the right, so we approach x equals negative 5, we're getting closer and closer and closer to a value of negative 4. In that case, it does hit negative 4, but it doesn't matter. We just care what's happening right around negative 4. And then the limit as x approaches negative 5 of the function, because these two are not equal, this does not exist. That's that theorem that we just talked about. Okay? Moving over to negative 1. Limit as x approaches negative 1. Okay, that's right here. Well, we are approaching the same thing from both sides, so the limit does exist, and the limit is 2. Okay, another one-sided limit, the limit as x approaches 2 from the left. Okay, as we approach 2 from the left, we're coming down this way. We are approaching, again, doesn't matter that it doesn't exist, we're approaching a height of -3. Okay, as we approach from the right, we are also approaching a height of -3. Okay, the limit as x approaches 2 of the function then, because both of these are the same, this limit does exist. Or in other words, if we were coming from both sides here, our fingertips would just about meet right there, so the limit does exist. Okay, as x approaches 4, does the limit exist? Can we check from both sides? Yes, it does. 6. The limit as x approaches 7. Okay, again, we're coming down this way. We're coming down this way. Do not be tempted to jump up here. If you're moving along the function, your fingertip does not just jump up there at the last second. That point is not part of the limit, even though it is part of the function. So what are we approaching? We're getting closer and closer and closer to -5. Okay, and then the limit as x approaches 10 from the left. That's coming this way. We're approaching a height of 1. Again, doesn't matter that we don't reach it. As we approach 10 from the right, well, there isn't anything to the right of x equals 10, so this limit does not exist. Okay, and so because these two are not the same, even because it only exists from one side, the limit as x approaches 10 does not exist either.